Hello and welcome to lecture 2 of this course, Symmetries, Particles and Fields. So in this lecture, we're going to get into some basic definitions of groups. It's only going to be illustrated with finite groups. So we're going to start off defining an equivalence relation, then the direct product between two groups, automorphisms, and the semi-direct product. So if you've seen all these things, you can skip this lecture. Okay, so this is just a plan from the end of last lecture. So we start lecture 2. And this will be a reminder, or perhaps some of you will be seeing it for the first time, about the equivalence relation. Okay, so an equivalence relation we write as this squiggle, or a tilde. So this is a relation on a set. So on a set big S, it has 3 properties. Firstly, it's got a property called reflexivity. So here, an element of the set, every element of the set is equivalent to itself. There is a symmetry property such that if 2 elements are related by this equivalence relation, then effectively, well, if the first one is related to the second one, then the second one is related to the first one. So this is for all elements of the set. And thirdly, we have transitivity. And what this means is if we've got 3 elements and elements 1 and 2 are related and elements 2 and 3 are related by the equivalence relation, that means that elements 1 and 3 are related. Okay. So we write the equivalence class of some element in the set with square brackets. So the equivalence class of some element little s in the set big S is written as square brackets around little s. And this is the set of all elements in S that are related by the equivalence relation. Now, equivalence classes are important because they partition up sets. And the way that we find this out is that we show that 2 equivalence classes are either disjoint to each other or equal. So we're going to prove this now. So we take 2 elements of the set, S and S tilde in the set. Either they have no elements in common, So their intersection is the 0 set. Or there are some elements in common. And so let's take one of those that is in common, S prime. So this is in the union between the two. Then for another element of the set, another element in the set which is in the equivalence class of this first equivalence class. So in other words, we have S prime is equivalent to S double prime. By symmetry, this means that S double prime is equivalent to S prime. And this means by transitivity that S double prime is in, it's in the union between these two sets. So S double prime, is related by the equivalence relation to this element S tilde. Now we can work this argument completely backwards. So and vice versa. So in other words, in this case, S is equal to S tilde. So the equivalence classes are the same. So equivalence classes partition up sets. What I mean by that is we take our set S and we could have, varying numbers of different equivalence classes, but because they're disjoint or equal, we can add them all up and get the set to S. So let's take an explicit example. Let's take the set of all integers. And then let's say that the equivalence class is if S mod 2 is equal to S prime mod 2, then they're equivalent. And here there are two equivalence classes, the even and the odd integers, of course. So we can pick any element of each to represent the equivalence class. So the equivalence class of 0 is the set of all even integers, and the equivalence class of 1 is the set of all odd integers. All right. So now let's take the subgroup of a group. So a subgroup H of a group G. It's a subset of G, which is also a group. In other words, it satisfies the group axioms. And we write it in this form. So we have the set language that H is the subset of G. So we can define an equivalence relation between two elements of G using this subgroup. So let's take an element Gi and one Gj. And we say that they're equivalent, well, there's this equivalence relation between them if and only if Gi is related to Gj by an element H for some element little h in the subgroup. So that defines an equivalence class. Each equivalence class defined in this manner is called a coset. And it has the same number of elements as H, big H. So remember, in a finite group, at least, the number of elements is the order. So the order of some group is written by the same symbols that one uses to describe the modulus or the absolute value. So the order of G is written with these vertical lines. So the cosets form a coset space. So this is written G/H. And it's such that G/H is isomorphic to G with the equivalence relation. So in general, this coset space may or may not be a group. Okay, so we want to define a different kind of subgroup or a subset of the subgroups, which is a normal subgroup. It's also sometimes called the invariant subgroup. So a normal or invariant subgroup H in G is defined such that G, H, G to the -1 equals H for all elements of G. Now, what does this mean? I've written elements of a group G on the left-hand side, but I have the whole group, subgroup H written here. So notice that the element of H on the left-hand side and the right-hand side can be different. That's what that equation means. So in this case of a normal subgroup, then in fact, the coset space is G over H is a group. So we can see this by the following. Let's take Gi prime, which is Gi-Hi, and Gj prime is Gjhj, with the obvious notation, Hi and Hj are in the subgroup. So what this means is that Gi prime, Gj prime is equal to Gi, Gj times H for some element H in the subgroup. So there's a one-line proof of working that you can do yourselves as a small exercise to prove that. Okay, another definition we need is that of a simple group. This is important, actually. So, well, all of these definitions will be used at some point. So a group is simple if the only normal subgroup are, as a group G is simple, if the only normal subgroups are the trivial subgroup given by the identity so it's a set of just the identity and the group itself. Okay. So the center of a group So this is written calligraphic Z of G, where G is the group. This is the set of all elements which commute with all elements of G. It's an abelian normal subgroup. You can check those properties for yourselves if you like. So if we have two groups, we can form another group from these two, kind of a compound forming of it, and it's called direct product. The two groups, G1 and G2, we may form a direct product group. So we write it G1 cross G2. So this is formed by pairs of elements. So it's the set of all pairs of elements G1, G2, where G1 is in G1 is in big G1 and G2 is in big G2. And such that we have the following relations. So if we consider group composition of this direct product, so let's take the product of two elements, so it's of course the product of two pairs of elements, then we just do the simple thing, which is we take the composition of the pair within the respective groups. Oops. Then, and we have that the inverse element of this pair is just the pair of the inverse elements. And, you know, the identity of the direct product group is really the identity of product group, of the first group, and the identity of the second group, but written as a pair. So if it's clear which elements belong to G1 and G2, as for example might be the case when G1 and G2 are different groups, then you can just write, there's a bit of nomenclature. Instead of writing these brackets and the comma, you might just write them next to each other. So, so long as it's clear which elements belong to G1 and, oops, big G1 I should say, first group, and which to the second group, we may write pairs as just G1, G2, instead of the brackets and the comma. So for finite groups, the order of the direct product is just the product of the orders. So we have another object which is important, and it's the commutator. So if we take some particular group and two elements of it, G and H, so we have this object which is called the commutator, and this is defined to be, okay, so we put G and H in square brackets with a comma in between them, and this is defined to be G to the -1, H to the -1, G, H. So if the result of this operation is just the identity element, then we say that the two elements commute, G and H commute. So, okay, there's another bit of nomenclature. If G is abelian, well, G is abelian if and only if all of the elements commute, basically. Okay, so now I want to just quickly talk again about some cyclic dihedral and permutation groups, just to give you a little bit more background on finite groups. Okay, so cyclic we've seen. So for example, Zn. So this is an abelian group. And for prime n, it's a simple group. The dihedral group, well, we saw this for the triangle, and you've done an exercise in it, hopefully, for the square, symmetries of the square. So in general, Dn is the symmetry group of a regular n-sided polygon. In a two-dimensional plane, formed by rotations through 2 pi m over n, together with a reflection r. So what we're going to do is define dn as, so each of these rotations of 2 pi over n is a, and so we can take a to the m, or a to the m with a reflection, where m is in the set 0 to n minus 1. And we have a to the 0 is the same thing as a to the n, which is the identity. We have reflection squared as the identity, and we have a times r is r times a to the n minus 1. Okay, so m has n possible values, and we have these possible, we have n of each of these members of the set, and so the order of the dihedral group is 2n. And you can notice various things about these. If you think about it geometrically, you'll be able to convince yourself that a to the m composed with a reflection first squared is the identity, for example. This makes sense if you think about it geometrically. So for n bigger than 2, in fact, AR is not equal to RA. And so the group is non-abelian. It's got products in it which do not commute. In other words, permutations. So here, this group is Sn, and it's the number of orderings, number of different orderings of n elements. And so the order of Sn is n factorial. And in fact, S3 is isomorphic to D3, for instance. And you can see this by the fact that you can label D3 by numbering the vertices of the triangle and seeing all the different permutations of those vertices as being different elements, symmetries of the group. So numbering the corners of the triangle. Good. All right. Now I want to go on to another topic, which is to define automorphisms. These are maps of the group elements, which where the product rule, the group product rule, is preserved. So an automorphism, automorphism of a group G set of some elements is a mapping between elements so each element Gi goes to some map which we call phi of Gi, such that the product rule, the group composition rule, is preserved. So in other words, phi of Gi, phi of Gj is the same thing as taking a map of Gij. And this is for all elements of the group Gi and Gj. So we write this an automorphism as G with this mapping phi as a suffix, and this is equal to the set of all elements phi of Gi. So this is isomorphic to the original group G. So in order to preserve the product rule and the group axioms, we must have that the identity maps to itself and the inverse of a group element maps to has the inverse map to the element. So for some fixed elements of the group, you can define an inner automorphism. So we pick particular elements of the group and we define what's called an inner automorphism. By phi little g suffix of Gi, and this is just defined to be G times the elements of the group you're looking at times the inverse of G. Well, with the group product with the inverse of G. And if you have an automorphism which isn't an inner automorphism, it's called an outer one. Okay. If it's not inner, an automorphism is called an outer automorphism. So the set of all automorphisms forms a group. We can write this as aut G. And so it turns out this must include the coset space of G and its center as a normal subgroup. So let's just take a really simple example of an automorphism. Let's start off with Z3 being E, A, and A squared, for example. And now we can take some map of these elements to be E, A squared and A. So we just switch around the A and A squared. And so here, basically because you've got two options and because one turns into the other, the automorphism group is just Z2. And Z3 divided by its center is the trivial one element group given by the identity. Okay, good. So we've been mainly introducing these automorphisms because we need to define a new kind of direct product, because Poincare representations of groups use these this particular kind, and it's called a semi-direct product. So we can use an automorphism to define a new product or a new kind of product group between the automorphism and the group. So let's take some subgroup H, which is one of the automorphisms, basically. So it's in the automorphism group of G, such that for any element of it and any element of the original group, we have that G is mapped with this particular element H to some map which has a suffix H of G, and this map is defined such that, of course, phi H G1, phi H G2 is phi H G1 G2. And phi H1 phi of phi H2 G is phi H1 H2 of G. Phi of H of E is just E. So E is always mapped to itself. And if we have the map corresponding to the identity, we just get back the same element of the group. And we have that the map of some element that corresponding to some inverse element H is just the map corresponding to the element, and it's the inverse map. So if we have all these, we can form a new group and it's called the semi-direct product group. And a semi-direct product of H with G. And it's denoted almost like the direct product, but with a little line going on the side of the automorphism. Okay, and it doesn't matter, as long as you get the line on the automorphism side, it doesn't matter which way you're doing it. We're going to stick with this first way of writing it. So as with the direct products, it's defined in terms of pairs of elements. So H and G, and they belong to big H and big G. But now the product rule is less trivial. So this is the important rule, the product rule. You can derive the other stuff from this. So if we have two elements of this semi-direct product, then we get what we would have with the direct product in terms of this subgroup. But we almost have G times G prime, which is what you would get for the direct product, but you just have this automorphism twist in the second, in this. So it's G composed with this automorphism twist of G prime. All right, so you can convince yourself that the inverse element is equal to h to the minus 1 and phi h to the minus 1 of g to the minus 1. That will come out in one line if you just multiply it by the thing where it should give you the identity. And you can check for yourselves. Now again, it's a one-line proof that the following equality is true. So you just use the rules been given to you. It's annoying that happens. Okay. That'll be better. Right, and also you can also show, so this is 1 and 2, you can also show that the following is true. If you have trouble with these, look in the book. They're written out in full there, or at least more detail is given. So let me check I've written that right. Yeah. So what this means is that G is a normal subgroup. If you look and see what the definition of normal subgroup is, this means that G is a normal subgroup of the semi-direct product. And that has the implication that H is isomorphic to the semi-direct product coset space with G. As I say, this is important for representations of the Poincare group, but let's just see a simple example with our dihedral group. So actually, this is isomorphic to the semi-direct product of rotation of reflections with rotations. So Z2 is just E and R, where R squared is E. And Zn we've seen before is A to the M, where M is in 0 to n minus 1, and A to the n is the identity. And we define for any G which is A to the M in Zn, we define our map phi r of G is G to the minus 1, which is RG R to the minus 1. You can check all that out for yourselves in your own time. Okay, good. So that's all of the basic definitions. Sorry, it was a bit dry, this lecture, that we're going to need about groups in general. And next time, we're going to get on to do in lecture 3 the basics of Lie groups. And so we're going to set them up. There are matrix groups, and so we can use a lot of the machinery that we're used to in terms of matrices to define these groups. And that's actually going to be very helpful for us all the way through the course. See you next time.